So we've described a little bit about what radio pulsars look like and how they operate. And we know that we have this radio emission coming from the magnetic poles. We also saw just now that the radio pulses can be very variable from one pulse to the next. It's also important to remember that the vast majority of pulsars are not bright enough for us to be able to detect those single pulses. Okay, but that is changing, of course, as we get more and more sensitive telescopes, but we'll also be finding more and more fainter pulsars. So what do these radio pulse profiles look like, and what can they tell us? Well, you can think of two different modes or two different options for what you might see. In the bottom half of this slide, you can see two different cartoons, one on the left, which we call core and cone, and the one on the right called the patchy cone. And here what we're doing is we're simulating looking down on the magnetic pole. Okay, so assuming we could stop the pulsar and we're looking down on the magnetic pole. And what I'm going to show you in the top plot is different pulse shapes that we get when we average many hundreds of pulses together. Okay, so these are the stable average pulse profiles that I mentioned before. So if we have our line of sight follows the gray lines that just passed onto the screen, you can see there are two options. One where we pass this so-called outer cone region, or one where we pass through one of these patches. And you can see that that gives us this smooth, almost Gaussian shaped pulse profile that is seen for this particular pulsar B1642-03. Actually, I'll pause at this time to try and explain to you the names of pulsars and what they mean. So PSR, of course, stands for pulsar. The B refers to the epoch of the position that we're going to use for its name. The 16 is the right ascension of the source. The right ascension in hours. 42 is the right ascension minutes. And the -03 is the declination in degrees. You'll see that these are all B-named pulsars. This means that they were probably discovered very early on. Since around about the late 1990s or to mid-1990s, all newly discovered pulsars are given what's called a J name, which refers to the J2000 epoch. And if you see a J name, then it will have the J, then the right ascension hours, the right ascension minutes, the declination degrees, and then also the declination arc minutes. Okay, so we'll have 8 digits. Okay, so basically a pulsar's name is its address. Right, on to the second pulsar we're going to look at here. This is pulsar B2020+28. And we can think of it having a sight line, something like the blue line that's shown here. So here we can see it passes over two edges of the cone, but it misses this other cone here. So we just see two peaks like this. And by comparison, in the patchy cone case, it would pass through two patches on the magnetic axis or on the magnetic pole. And then you can have more complicated pulse profiles like this one, 0809+74. Oh, actually, sorry, I see that's wrong. That should be 1257+25. I apologize for that. And it has 5 components at least. And you can see in the core and cone model, you can model it as passing through this side of the cores, through the cone region, and then through the other side of the cones. In the patchy cone case, we can see that it passes through the edges of 5 separate patches to give you this complicated pulse shape. So these are different pulse profiles that you can get from pulsars, and what we think it might be like, or the regions that are generating the radio emission might look like. It's fair to say that probably the core and cone model is considered to be more popular these days, but there are many caveats about which of these two models might be more appropriate. I mentioned to you about these average pulse profiles and the earlier about when I showed you the pulses from 0329 plus 54, you can see how they vary. Not only do they vary in their shape, sometimes they can vary in a very organized way in terms of where they arrive. So you can see here for 1642 minus 03, these are individual pulses. So each one of these lines in this direction is a pulse of the pulsar. We zoomed in, so we're only showing one subfraction of the total rotation period of the pulsar. But you can see that it moves to the left and then to the right and then to the left again and wiggles around. Okay, so on average, each individual pulse is narrower than the average pulse profile that we get. By comparison, you can see that this 2020 plus 28 is showing very strong pulse-to-pulse modulation. You can see sometimes the pulse is very, very bright, but you can also see that it's not equally bright on both of the components at the same time. And this might be one idea that supports the patchy model, for perhaps. Or it says that those core and cone things are actually made up of different subpulses and not just being smooth cones like I showed in the cartoon. On the right-hand side is a very special type of structure that is seen in the individual pulses. And these are the so-called drifting subpulses. And you can see that relative to a fixed point, they appear to be arriving later and later as we go on in pulse number up here. So this is time increasing in this direction, and each one of these lines is a new rotation of the pulsar. And you can see that this period repeats approximately every 11 rotations of the star. And so this is perhaps telling us that things are very dynamic in the pulsar emission region. And maybe these little entities that are doing the emitting are actually rotating themselves around the magnetic axis. And these are called drifting subpulses. There's all sorts of other pulse phenomenology that we know about, and I can't spend long on it, otherwise basically you would end up doing your PhD. But just to highlight some of these things, there are relatively recently discovered objects called RATs. They are now nearly 15 years ago that they were discovered, but basically they give off only 1 or 2 pulses every few hours. So the rates of pulses is a few per hour or less. Okay, and so instead of every rotation of the neutron star, you see a pulse, pulse, pulse. We actually only get a pulse every now and again. And it might be that this is because of the nature of the emission, or that, that they are somehow turning on and off for some other reason. We now think that these are probably just some extreme end of the normal pulsar population, but they are an important aspect of pulsars. There are other pulsars which we call nullers. And what that means is that a fraction, anywhere from a few percent to maybe 90% of the pulses will, of the rotations of the pulsar will not result in a pulse of radio emission. So here we've turned the normal pulse stack that I showed you on the previous slide on its side. And so time is running in this direction. And this is the pulse window here. And you can see that there are pulses, groups of pulses here, but then in between those, there are so-called nulls, okay? And the distinction between RATs and nullers is sort of subtle in some cases, because of course, an RAT, you could argue, is an extreme nuller. There are also other pulsars called intermittent pulsars. And these can be on for days to months. So every time you look at it, it'll be there, it'll be on. But then for a period, it can be off for a few days or months, and then it'll turn on again. And some of these objects are actually highly periodic. So they will be on for a few days, then they'll be off for maybe 10, 15 days, and then they'll be on for a few days, off for 15 days. And so that's actually quite strongly periodic signal. And these objects have actually taught us a lot about the emission physics of radio pulsars, because we get an opportunity to look at the source when it's on and see how it spins, but we can also see if it spins any differently when it's off, and it turns out that they do spin differently. More types of pulsars are known. There are these so-called giant pulsars, which can be hundreds to thousands of times brighter than the normal radio pulsar emission. And only a handful of the sources are known to emit them. And all of those sources are known to be also emitting at high energy, so at X-rays, for example. The plot here is for the Crab pulsar, and you can see here that each of these little spikes is one of these giant pulses, or they go to make up a giant pulse. And the finest structure that we have measured so far in any of these objects is narrower than 2 nanoseconds. So that's incredibly tiny. We're resolving a feature of less than a meter in size somewhere in that pulsar emission region. There's also microstructure, which is shown here, which has these strange shapes, and not seen in all the pulsars. Sometimes it's quasi-periodic and may be associated with a fundamental emission mechanism. And then there are these other ones which we call spiky emission, and sometimes they're very narrow and bright. And this is somewhat reminiscent of what we see from RATs, except we don't see the source being distinctly off, but we certainly see it being much weaker sometimes and then much brighter at other times. So these objects are very varied in their radio emission, and you can understand therefore why it's been challenging to try and come up with a complete model of the emission physics of these objects. I just wanted to highlight one particular pulsar just to give you an idea of the nature of the sources that we're dealing with, and just to give you a flavor. So the Crab pulsar, it's associated with the Crab Nebula, and it's a very young pulsar. We believe that the supernova which formed this pulsar actually occurred within human history. So in 1054 AD, we believe there was, well, we know that there was a so-called guest star seen by ancient astronomers around the world, in fact, but most commonly known in China and in Japan, but others are known to have recorded this event. And so this was the supernova which generated this pulsar. It's got this rotation period of 33 milliseconds, so it rotates around about 30 times per second. As I said, it's young, it's about 1,000 years old. It's at around about 2 kiloparsecs away. And it's young and it's energetic, and so it emits across the entire electromagnetic spectrum. It's seen emitting in gamma rays, high energy tera electron volt energies. It's seen emitting in the optical. And so you can see in this top right-hand plot, we show the pulse profile in all of these different energy ranges. So you can see in the radio, it's got a complicated profile with a main pulse, and it's actually got an interpulse, which means that we're seeing both the poles. It's also got, this is the optical emission here. Here are the X-rays, and then we go all the way up into the high energy gamma rays, and then up to giga electron volts. And on the far left-hand side, you can see this beautiful Chandra image in the X-rays of this pulsar. And what you can see is the neutron star shown as this dot here, but then there's all this, there's a torus where the wind is interacting, the wind from the pulsar is interacting. It looks also like there are these jets being emitted from the pulsar. And so we can see that it's a rich, rich environment here around this neutron star. So there are around about 3,000 radio pulsars known, and they emit pulses of radio emission, which require generally, for the vast majority of the sources, the largest radio telescopes in the world to detect. And you can see here an animation showing the Lovell telescope at Jodrell Bank, where we observe around about 800 of these pulsars on a reasonably regular basis. If we take these pulsars, we can put them in a diagram which is called the period derivative diagram. So on the x-axis, we plot the log of the period, and we plot something called the period derivative here, the log of the period derivative. Now, all pulsars, apart from those that are in globular clusters or are accreting material, and we'll come back to the globular clusters a little bit later, they are slowing down. Okay, so their spin period is getting longer with time. And this is because they emit magnetic dipole radiation. So basically, if you take a dipole, a magnetic dipole, and you spin it in a vacuum, it radiates away energy. And so it will spin down, it will get slower and slower. And that's what's happening to our pulsars as well. And so we can use this to try and identify different types of pulsars and group them together. So it's a little bit like that Hertzsprung-Russell diagram that I showed you right at the start, but this time it's for pulsars themselves. So you can see this main island of objects here in the middle of this plot that have periods of around about 1 second, and they have spin down rates of around about 1 part in 10 to the 15, or 1 times 10 to the minus 15. Now we can use those two values to make an estimate of the magnetic field strength. And you may come back to this in the exercises this afternoon. But basically, the vast majority of pulsars have a magnetic field strength of around about 10 to the 12 counts that I mentioned. Over here in the left-hand side, these are the young pulsars. So these are pulsars that are associated with supernova remnants, like the Crab pulsar I mentioned before, and they're thought they are very energetic. Up in the top right here, we have again a relatively new class of neutron star. They're called magnetars. They spin very slowly, so they have spin periods of 10 seconds approximately. They have very high magnetic field strength. You can see that they are up at around about 10 to the 15 Gauss. And they are not powered by their rotation. Okay, so previously I said that these magnetic dipoles, these pulsars are basically magnetic dipoles, and they're slowing down. And what we think happens is that some of that energy is transferred into the radio emission that we see. In the case of the magnetars, they're mainly seen as gamma ray and X-ray sources, and they are so bright that there is insufficient energy from that spin down or the slowing down of the pulsar to generate the emission that we see. And so what we think happens here is that the magnetic field itself is being distorted or affected, and that is generating the emission at high energies. Some of these sources have been seen in the radio, but the majority are not. They are also tend to have outbursts, so they're not always active or visible. We have this other region in here, which are the so-called double neutron stars. So these are systems that I hinted at earlier, where not only do we have one star that was massive enough to go supernova, but we had two stars that were orbiting each other. One went supernova, formed a neutron star, which became a pulsar. That pulsar probably aged, and then it accreted material and was spun up. So spun up to a period of around about 70 to 100 milliseconds. And then what happens is the other star eventually also goes supernova. And if it's massive enough, it formed another neutron star, and it's a pulsar. So then, depending on when you catch the system in its evolution, you could have a slow pulsar with a more rapidly spinning pulsar. But these slow pulsars live for only a few million or tens of millions of years. And so that it's not expected that you'll see many of these double pulsar systems, but we definitely see systems where we know there's two neutron stars and one of them is active as a pulsar. And then in the far left-hand corner are those very rapid spinning objects I talked about at the start, which have periods down to 1.3 milliseconds. They have usually accreted material from a low mass companion. So their companions will be things like white dwarfs or brown dwarfs or things like that. They're usually in binary systems. So here you can see all of these ones with circles are binary systems. And you'll see that these binary systems are actually very rare in the normal pulsar population. And so this suggests that, you know, lots of these objects were formed, but only these ones so far have survived to become these millisecond pulsars. They spin very rapidly. They are the best clocks. And these are the ones that will be used for high precision experiments that we will talk about a little bit later on. So where are these pulsars located? So the vast majority of pulsars that we know about are in our galaxy. There are a handful known in the Large Magellanic Cloud and the Small Magellanic Cloud. And the reason why the vast majority of them are known only in our galaxy is that, as I mentioned before, they are weak radio sources. And so to find them at large distances requires extremely large telescopes. And so far, we've not found any pulsars outside of the most local galaxies. You can see here, this is a so-called ATOF projection onto the galactic coordinates. So this line along here that I'm showing you with my cursor is the galactic plane. And we're looking at the galactic center effectively from the position of the sun. And you can see that the vast majority of the pulsars, these black dots, are located in the plane of our galaxy. Okay, so most pulsars are located in the plane of our galaxy, which is not very surprising because that's where the vast majority of the stars are. So we need stars to form neutron stars, and that's why. You can see that the binary systems, which we know are predominantly millisecond pulsars, are sort of spread out more than the normal pulsars are. And that's because of two things. They're older, and so they've had more time to move through space. And because, well, actually mainly because of they're older that they're located there. Okay, so this is where most of the pulsars are located. I also mentioned about globular clusters. So globular clusters are these groups of millions of stars, and they exist in various locations in our galaxy. And because these millions of stars are located in a very small region, the density of stars is high, and you can have lots of interactions, and these interactions can generate neutron stars through explosions or the accretion that we talked about before. And so globular clusters hold a lot of the more rapidly rotating pulsars, the millisecond pulsars. I mentioned that these pulsars are extremely precise clocks. One way to think about this is that if pulsars were watches, they would lose just 1 second in 30 million years. Okay, so their accuracy is so high that they would only lose 1 second in 30 million years. In fact, the spin period of one of the most precisely measured pulsars known was this value at the start of this talk. And so what we can see here is that we have an extremely precise measure of the period. We can also measure the arrival time of the pulses, so the ticks of the clock, of the most stable pulsars to 50 nanoseconds. Okay, so just to remind you, that's 50, 1,000, 1,000, 1,000ths of a second. And so any small change in the environment of the pulsar will change the time when the pulses arrive here on Earth. Okay, I think this is another good place for us to pause, and we'll come back after some questions or a break for a drink, and carry on with our tour of pulsars.